Okay, so example number 5, and we have a 100 horsepower, 200 volt DC compound motor, has an armature resistance of 0.031 ohms, a series field resistance of 0.012 ohms, and a shunt field resistance of 10 ohms. At full load, the motor runs at 600 RPMs and has an efficiency of 75%. Calculate input power, line, field, and armature current, mechanical power and torque developed by the armature, total of the copper losses, and the constant or mechanical losses. Now, this one is an interesting one because when you're given the efficiency of the motor, you're not given E0, you're not given IA, you kind of got nowhere else to start except for with the efficiency calculation. And so whether or not I ask you for input power as part A, that's still your approach. And so remember that if I asked you part A, line, field, and armature current, the way you're going to find the line current is from the input power, because input power Pn is equal to E source times I line. And then you can find the field current and the armature current from there, right? And so the idea is that once you have the armature current, the stuff gets a lot easier. But if you're not given IA or E0, and you are given the efficiency, that's pretty much your approach. And so for these types of questions, you always got to look at the similarities between, the different questions. They all got different values, but there's only 2 or 3 different, approaches for starting, shall we say. Now, again, we needs an equivalent circuit. And so for the equivalent circuit, then this is it. And again, now we'll copy that and put it back on our question page. And I need to resize. Okay, so then that looks pretty good. Now, our equivalent circuit. Remember that when we are given our ratings, they are mechanical output power, so we've written that over here, body armature, P out 100 horsepower. When we have 200 volts given as a rating, that's always the source voltage, so ES 200. So those ratings go opposite sides of the circuit, and it's very important for you to remember that. It's a compound motor, and so you notice this one is again a compound motor, but we've been given values of armature resistance and series field resistance separately, right? So different from that last question. And so armature resistance 0.031, put that by RA. Shunt field resistance, series field resistance 0.012 ohms, put that by RSE. And then a shunt field resistance, which is usually a bit bigger because it's in parallel instead of series, 10 ohms. So I've included the rheostat. That's not really necessary, but I usually do. And we got our shunt winding symbol, and 10 ohms represents, remember, that total resistance of that whole shunt circuit. Okay, so there's our numbers. Now the other thing, then, this is a compound motor. We should label the currents. There's 3 of them: I line, IF, IA, and we should label E0 next to our armature. Okay, so then that, completes the armature circuit. Completes the equivalent circuit. It has all of the values, except for, well, the speed and efficiency, I suppose. They don't really go on the circuit, but it got all the values on the circuit in the proper spot. So there's your starting point. Next, figure out what you've been asked to do. Okay, so we have input power, and again, we listed those out, so we know what we're asked to do. And so now, analyze the circuit. Well, analyze the circuit means, let's see, don't have a line current, don't have any currents, don't know E0. I got to start with my efficiency because I do have P out. And so that's where we'll start, right? Okay, so part A. P in. What do we know about it? Well, it equals E source times I line. We know that. But again, we don't have any currents here. If we add IA, we could find I line because IF just comes from Ohm's law. And so, but we don't have IA, we don't have I line. and so we can't really use that. Okay, so where else does the input power show up? Only one other equation, and oh, it keeps losing my cursor. I never had that problem last day. So if efficiency is equal to P out over P in times 100%, then that's where we're going to find our P in from. And so what I'm going to do now is I'm going to write efficiency as a percent, so 0.75%. I'm sorry, 0.75 is our decimal value. So we're going to write it as that. So we're going to ignore the times 100%. And we're going to say then, from this efficiency equation, I can say that P in is equal to, I can switch their places, right? P out divided by the efficiency. And so remember now that P in got to be bigger than P out. And so that'll help you get this correct, I hope. And we have 100 horsepower, which of course, you know, we got to put that in watts for electrical calculations. So times 746 watts, and you got to know that number, right? Over 1 horsepower, and we're going to divide that by the efficiency as a decimal, 0.75. Now, and so again, right, horsepower cancels with horsepower, and the unit that we're left with is watts, and so that's very important. And so that becomes 7,460 watts divided by 0.75. And so now that means that if we do that calculation, P in is equal to, we comes up with, if we round it to 3 significant digits, 99.5 kilowatts. And so, you know, I'm bad with K's. Even if I was doing this on the board for you, I got a job to distinguish between a lowercase k and uppercase K. So my K there looks like uppercase K, but for kilo it should be lowercase. Not a big issue, I suppose, but really, you know, should be lowercase. Okay, so now part B. Yeah. Okay, and so yeah, I got a mistake. Because if I multiply 746 by 100, I got to add 2 zeros to it, right? Only put in 1, didn't I? And so we got that, right? So that's 74.6 kilowatts, or 74,600 watts, isn't it? Yeah, so then that gives you 99.5 kilowatts, right? Okay. Now, and so part B, now we think about, you know, circuit analysis. We got this formula here, P in equals ES times I line. And so we can start off now with that, or IF is generally comes from the equivalent circuit, because we have the source voltage across the shunt circuit here, and that's pretty much all the time. And so you know, that calculation hardly ever changes. We got ES divided by RF, and so that gives us 200 volts over 10 ohms. And so IF equals 20 amps. Now, next, from, and I'm going to erase that, but from Pin equals ES times I line, we're going to say that, you know, from this equation now, we can say that I line is equal to Pn, and if I move ES to the other side, it goes under, so I got Pn divided by ES, and I got 99,500 watts over 200 volts for ES. That should be an S there. And so if I does that calculation there, comes up with 497 amps. Now there might be some rounding there, but I'm trying to round it to 3 significant digits, right? And so we got 497 amps for our line. Now, so if we write Kirchhoff's current law at the node here, we're going to say that I line is the current that enters. It equals the sum of the currents that leaves, and so that's IA plus IF. And so that means then that therefore IA equals I line subtract IF, the difference between the two. And so again, I line got to be the biggest current. It divides into IA and IF. We have 497 amps. Subtract the 20 amps that went into the field circuit, and IA then has a value of 477 amps. Any questions about that so far? Okay, so now we're kind of running out of room, and so I'm going to have to scroll down, and so we're going to lose that equivalent circuit for a second. Maybe I can, let's see now if I can hard equivalent circuit down a little bit. Yeah, it's probably going to let me do that, so I'll pull that down a little bit. We might be able to keep it on the screen that way, I'm not sure. For some of it anyway. And so now okay, we'll go that far for now. And so part C now, we want mechanical power and torque developed, right, by the armature. And so remember, the mechanical power developed is PMI, and PMI equals E0 times IA. And so I got that written as EA, And so let's not confuse that, because EA, it might be VA, right? And so it's E0. And did we calculate E0? I'm thinking we got the information for that, but we didn't calculate E0. So we got to go back and find that first, right? Okay. We need to find the value of E0. E0 is equal to the source voltage, subtract the voltage drops in the armature circuit, and this time when we write in RA plus RZ, we got two different values in the brackets, right? Because they've been given to us separately. And so now we have then ES at 200 volts. Subtract A at 477 amps, and our resistors at 0.031 ohms plus 0.012 ohms, and if you add those up, we have 0.043 ohms, 0.043 ohms, and so then E0 becomes 200 volts. Subtract the voltage drop in the armature circuit, comes out to be 20.5, and that gives us E0 then at, and I think I just went and put 179.5, and I didn't round that to 180 volts for E0. So now back to PMI, and so now we have 179.5 volts, and our A was calculated as 477 amps, and so the power developed by the armature PMI was equal to, and then that calculations comes out to be 85.6 kilowatts. Now we expect that then to be bigger than P out, don't we? And when we said P out was 74.6 kilowatts, and so that gives us a constant loss that we can certainly calculate. Now we're also in this one asked for the torque, and I'm sorry about the mess I got made there, but if I'll pull the torque over here now, T again developed, the definition, right, talks about torque developed, and so when it's as defined, torque developed, it means that we're using PMI as the power developed by the armature, and that gives us the torque developed. P out is less than PMI, which means the torque output is generally less than the torque developed, right? And so PMI here, and in, so we have 9.55, and our 85,600 watts, and divided by, and I'm going to have to pull that down a bit. The speed was given to us in the problem as 600 RPMs, And so and that means then that the torque developed is equal to 1300, and I just left it at 63. I remember that the unit for torque, the SI unit, is Newton meters. Okay, now the very last part of that said, oh no, a couple of parts left yet. Okay, so we should have enough time there to finish it. I keep losing my cursor. And so part D, now let's think about part D. Part D says the total of the copper losses. And so we know that the copper loss now is equal to, right, the loss in the shunt winding and the loss in the armature winding and the loss in the series winding. And we found IF and IA, and so we can do these three calculations separately, and then we can add them up. But remember that we're not asked for them separately today. And so the copper loss is also equal to Pn, which we know, subtract PMI, which we also know. So a little bit faster, easier for us to say that Pn was 99. If I could draw that second 9. Point 5 kilowatts, subtract PMI, which was 85.6 kilowatts. And you can, check the math there and show that that agrees with IF squared times RF, IA squared RA, and IA squared times RC, or IF squared times RF plus IA squared times that 0.043 ohms we had up there. And you can, verify that that calculation gives you the same value. And so the total of the copper loss then at 99.5 kilowatts, subtract 85.6 kilowatts, we have 13.9 kilowatts. And again, that got to be the easiest way to do that calculation. Now for part E, we are asked to find the constant loss. And so the constant loss, remember, is the mechanical loss, or also might be referred to as the shaft loss. And that one is on the other end of the motor, right, across the shaft. And it is the difference between PMI and P out. And so we have for that PMI, which was 85.6 kilowatts, subtract P out, which was 74.6 kilowatts, right? We had 74,600 for that. So 74.6 kilowatts. And so that constant loss then, if we do that calculation, 85.6 minus 74.6 is equal to 11 kilowatts. Now, If you took the 13.9 and added to the 11, you get 24.9 kilowatts, and that is the total loss in the motor. And that should be the difference then between P in and P out, and so you can check that calculation too, right? Okay, so I'm going to stop that recording now.